Okay. Well, don't know how many we're going to have today, but we'll go ahead and get started. All right. Let's see. Let me share my screen. Kendall and Peyton. Let's see. Okay. I think I got everybody now. All right. Okay. All right. So today we're going to wait. Yeah, my mic is on. Okay. Today we're going to wrap up the gases part of Unit 5. And then tomorrow we'll start into dealing with heat, so thermochemistry part of it. So we just got a couple little wrap-up topics today. And then we can look at the Jamboard if there's some problems with the quest assignments that people had. Okay, so let me share my screen. We're working with that same set of notes. Okay, here we go. All right, so the first thing, we sort of mentioned this the first day, but we didn't really focus on it. But kinetic molecular theory, and this, the equation we've been using, the PV equals nRT, that's the ideal gas law. And so an ideal gas law, we consider it ideal if it basically follows those equations, if we can use those equations to predict its behavior. And the kinetic molecular theory, those are the assumptions that we make in order to be able to use those equations. Okay, so these equations are kind of simplified versions that under certain conditions they work. All right, but these are the assumptions that are made with those particular for those gas laws. So the first one is the volume of the individual particles is 0. And what that means is that usually compared to the volume the gas is in, the size of the individual gas molecules is just not even significant. It would be, if we tried to account for that, it'd be way out in the decimal places. So we are assuming that relative to the volume that the gas is in, the size of the gas molecules is just so small that we don't need to include it in our calculation. Then we did talk about this, that the pressure of a gas is due to the frequency of the collisions of the gas molecules with the container wall. The third one here, the particles exert no forces on each other. So what we're going to find out in the beginning of next semester is we're going to look at the attractive forces between molecules. And those forces, like in some circumstances, they do play a role in changing the frequency of the collisions of the gas with the wall. Because if they're able to attract or repel each other, then they can change the pathway of the molecules. And so what we're saying is that in these gas laws that we're using for ideal gases, that that any interaction between the molecules is just not significant. So we don't have to account for that. And then we did talk a little bit about this, that the average kinetic energy of the particles is directly proportional to the Kelvin temperature of the gas. Okay, and so that's why we have to use Kelvin in our gas laws. Our temperature is always in Kelvin. Okay, so here, okay. All right, so we're going to look at a couple of properties of gases. So diffusion is the mixing of gases through random motion. So even if we don't have, like, even if I didn't have force, like a fan or something going in a room, if I have a bottle of ammonia and I open it up, eventually anybody that's in the room would be able to smell the ammonia. And it's just because the gas particles are just going in kind of straight line trajectories until they hit something and it changes its path, but they're always moving. And so eventually they kind of diffuse throughout the room. Okay, so that's just they're moving around just through their nature of being gas molecules. Okay, so that's diffusion. The other type of movement we're going to look at is effusion. And effusion is like here where we have the gases in one side of this container and then nothing in the other side and a little pinhole. And again, this is through random motion. Eventually, through random motion, a gas particle is going to line up with that pinhole and make it to the other side. And so that's that kind of a movement. Both of these is just through random motion of the gas molecules. The key thing about this and their movement is that this is the one type of calculation where what the gas is matters. Because even if they're at the same temperature, they have the same average kinetic energy, but their speed, right? The rate that they are moving is going to be based on, I mean, their mass of the particle is going to have an effect on that. Something, if the higher the mass, if it has the same kinetic energy, it's going to have a slower speed to it. So these calculations, we do have to look at the molecular weight of the gas itself. All right, so this is Graham's law. And here, I don't know why on these notes it like didn't include these lines, but we need to put a dividing line there, a dividing line here, and this is a square root sign there. And then the same thing for here. Square root over square root. There we go. So essentially what this is saying is that the speed, like the rate of effusion or the distance traveled or the rate of diffusion, is they are inversely proportional to the square root of the molar mass. Okay. And that's coming from, I won't derive the whole thing for you, but you may be wondering, well, why is it the square root? If you look at the equation that looks at kinetic energy relative to the velocity or speed, it's K equals 1/2 the mass times the velocity squared. And so if you rearrange that and plug it into this, that's why we get the mass is, the relationship between the speed and the mass is the square root involved in that. Okay. All right. So we don't have to worry too much about that. We just need to look at using these equations. Okay. So here it wants the relative rates of diffusion if they're at the same conditions. All right. And I usually put the smaller one on the top because it's going to be going faster. And so if the ratio is going to be greater than 1, if the ratio is greater than 1, the one on the top is going to be faster than the one on the bottom. And so I don't know why it seems easier to think about it that way. But so what we're saying then is that the rate of the hydrogen relative to the rate of the bromine, okay, is equal to, and the square root of the mass of the hydrogen will be on the bottom, and the square root of the mass of the bromine is going to be on the top. Okay, so my hydrogen let's see, bromine is 79.9. Is that right? Yeah. All right. So 2 times 79.9. So I get the square root of 159.8, and then the square root of 2.016. Okay, so I get square root 8 divided by okay, so I'm getting 8.9. Okay, and so that means that the rate of hydrogen is 8.9 times faster than the rate of bromine if they're under the same conditions. Okay. All right. Okay, so here it's giving us, we have an unknown gas and then methane. So methane is CH4. Okay, so let's do the rate of our unknown over the rate of methane. Okay, it's going to be square root the mass of our unknown, square root the mass of the methane. All right, so here it's giving us the rates. So the unknown is 24.0 and methane is 47.8. So the square root methane is going to be 16.04 and divided by the molar mass of my unknown. Okay, so let's solve this. So we get 47.8 times, and then divide by 24. All right, so I'm getting that square root, the mass of the unknown is 7.98. And so I'm going to square both sides. I get 63.6. That would be grams per mole on that. Okay. All right, so which one will diffuse faster, NH3 or CO2? So NH3 is 17.03 and CO2 is 44.009. So the NH3 will diffuse faster because it has a smaller mass. And so if we want to do the rate of NH3 relative to the rate of CO2, and that's going to be, so the square root of 44.009 to the square root of 17.03. So I get 1.61. So the ammonia is 1.61 times faster than the carbon dioxide. All right. I think there's one more example problem like this. Let's see, Freon 12 to Freon. Okay, so I have Freon 12 to Freon 11. All right, so that rate is 107, 1.07 to 1. All right, and then that's going to be equal to we know the molar mass of the Freon 11. It's on the bottom, so its molar mass is going to be over here on the top, 7.4, and then the square root the mass of the Freon 12, which is what we don't know. Okay, so we got 1, okay, and that's going to be divided by 1.07. So I get that the square root of that mass is 10.9. So I'm going to square both sides, and I get about 120 grams per mole. And it wants to know which of these it is. And so I would just match it up with one of those. So let's see. Cl3, I'm gonna just look at the chlorines. That's going to be 70. So I have 3 of those. No, 3 is going to be too many. Maybe that one has 2. So 2 chlorines and a carbon and a fluorine. Nope, that one's about 10. It's about 102. So maybe it is. Let's see if I have 3. No, because that's going to make it 140. So let's try plus 4 times. Nope, that's too much. That's 154. Plus that's 137. Did I make a math error? And that's 4.
When you did the problem with 2 fluorine and 2 chloride, I think you only did 1 fluoride, or that's what you said while you were doing the math.
Okay. You're right. You're right. Okay, so this one does come out to 120. Okay. All right. So that would be, we would match it with that one then. Okay. Thank you. All right. Okay. So now let's go down a little bit. All right. And let's talk about real gases. Now, I'm going to show you an equation that is used for when the conditions are such that something about the kinetic molecular theory doesn't hold true. All right. And so basically what that means is that some of the factors that we were saying, oh, they're not significant, they become significant. And so we have to account for them basically through a more complex equation. This equation, actually calculating something with it, I think there's one quest problem where I do have you calculate using the ideal gas law and then using this more complex one, just so you can see the difference. But there's just one problem that I have you do that. Most of what you'll see on the AP exam that have to do with real gases is the concept of it, and, and the conceptual part about that equation. All right. So here's the key thing to think about is that gases aren't ideal whenever they are crowded together. All right, so that is like a small volume, which also correlates to high pressure. Okay, so high pressure, and when they are moving slowly, all right, and we think about average kinetic energy correlates to Kelvin temperature. So that's their low temperature. So we want to watch for, we get that non-ideal behavior, high pressure, low temperature. Okay, and so what happens then? Well, high pressure correlates to small volume. And so what that means is now the volume of the gas molecule does become important because it's relative to the container it's in, it has a significant value. All right, so that's the key thing about the high pressure. High pressures are achieved with small volumes, and so then the volume of the actual gas particles becomes significant. The other thing is when they're moving slowly, okay, so low temperatures, instead of when they're moving fast, they're just kind of zinging past each other. And so there really isn't an opportunity for those attractive or repulsive forces for them to interact with each other. But the slower they're moving, then the more likely they're going to like repel each other or attract each other, which means their paths get changed, which affects how frequently they're hitting the container walls on there. Okay, so that's why that becomes significant. So what you'll see, all right, is this thing, it's called the van der Waals equation. All right, and this is what it looks like. And so here, what we get is because the volume of the particle is important and the intermolecular forces are important, we have two values in there that are specific to the gas molecule. So these two factors we have in there now, and these, there are tables. So you would look up the gas and then find what the A and the B value of them are. And so the key thing to know about this is that A has to do with the attractive forces between the particles. And so a larger A means stronger forces. Okay. B has to do with the molecule size. So a larger B means larger molecule. Okay. And so again, you would just look those up. But in the quest, there are some conceptual type questions where maybe it'll list several molecules and say, you know, which of these would the B value be higher, or which of these would deviate more from the ideal gas law. And so the larger the molecule, the greater the deviation. Or with A, the stronger the attractive force, the greater it would deviate. Okay, and so here again, this is just showing, so this straight line represents like what we would have for an ideal gas, what the ratio between the pressure and PV divided by nRT would be. Okay, here you can see that as we get to lower or higher, higher pressures, we get a high deviation there. And then I thought I had a graph for the temperature too. But you would see something similar for temperatures, except for temperature, it would kind of be flipped in that your higher deviation would be on the lower temperatures. The higher the temperature got, the less deviation you would see on that. Okay. Any questions over this kind of thing? It would be probably a good idea to like maybe do a little study note again, since tomorrow we're going to start in on looking at heat and energy and how that relates to reactions. But you may want to just kind of summarize the key equations, that sort of thing, just to kind of have a study note there for that. Okay, let's see. All right, let me go to the Jamboard because I know there were this morning when I looked, there were some questions on there. Is it? Let me find the right one. There it is. Okay. All right. So let me check. I saw a couple of people that came in after I got started. Let me look again and just see. I got Field and Brady. Okay. All right. Okay, so I had, let's see. And I'm not sure who had posted the question, but anyway. But in looking at this one here, so for this one that had the burning the methane, and it gave you two, so it's a limiting reactant problem. And so the question was, what would you use for your moles? Here, do a BCA table. This is one of the ways BCA tables come in really handy, is that you just do your BCA table and you look at the afterline. And here, everything is a gas. So you're going to have some of whatever your excess is, you'll have moles of it left over. You'll have moles of carbon dioxide and moles of water. And so you're going to add all those together, and that will be the moles that you use in your PIVNERT to find your pressure on there. Okay. This one, and I thought I had done this one before, but maybe not. In this one,
you did it for me. It's somewhere on there.
Okay, let me go back then. But I think we only worked one part of it, right? Let's see.
Yes, I only had a problem with part 3.
Okay, so let me go back then and all right, so this one, everything is 1-to-1. So if we write out the reaction for this, right, we get, so part 2, we're putting water with SO2 and you're making H2SO3. Okay, and all right, so it's we have the water is going to be like our we have as much of it as we need here, or actually 5.9 liters. So you're going to look at, so that's going to be your volume, right? That'll be my volume. And then you're converting, let's see, what mass? No, you're converting the sulfur dioxide. So you'll go back up to that equation, which I can't remember what. Go back. I think we had that in here somewhere. That's not it. Oh, wait, I guess I missed it. Hang on. Wasn't that one? Wasn't. that one. Well, oh, here it is. Okay, so yeah, the balanced equation, let me write that down so I can move it. What do we have? 11O2 plus 4Fe2S2 yields 2Fe2O3 and 8SO2. Because I know I would not remember that. Go back here. Okay, so your equation up here, we had 11O2 plus 4Fe. Is it Fe2S2? I guess it is, yeah. Okay, Fe2S, Fe2O3, forgot the 2, plus 8SO2. Okay, so you'll go back up, which you would have used this reaction to.
Really, I don't think it's the Fe2S2. I think it's just
FeS2, okay. That makes more sense because then it'll be balanced. Okay, so you go back up to that and you'll get your, like, whatever your moles of the SO2 is. That's what you'll use with your 5.9 liters of water to get the molarity, and because it's all 1-to-1, so your moles of SO2 will also be your moles of your H2SO3 on that. Okay, and then it says, so this one, we had 100 or 1,000 kilograms, and then had 3 more zeros to get that to grams, times 0.05. Okay, so that's your FeS2. All right, so you're basically going to use that equation again with this much FeSO2, and you're going to assume your oxygen is the excess on that. Okay, and you'll do that to get your mass of SO2. So this is like part 3 is a completely new problem. The only thing related to part 1 in part 3 is the equation. But other than that, you're starting with new amounts on that. And then for the last part, then if in your BCA, you would have, oh, okay, this is asking for the mass. So you would use the same moles, use the moles of SO2 from part 3 with those conditions to solve for your volume of the SO2. Okay, and let's see. There was something. Okay, so all right, so this one we have, all right, gas A and gas B, and we have, it gives us a volume and a pressure, 430, and then here volume is 72 liters, and it's giving me a pressure of 856. Okay, so this one, right, we're going to do 2 P1 V1 over M1 T1. Okay, so first off, P1 V1 over N1 P2 V2 over N2 T2. Okay, so we're not changing the moles. We're not changing the temperature. All right, so that's the equation we're going to do, and we're going to do 2 of them. So you'll have your pressure 1, we'll say P1A, V1A, okay, is equal to P2A and V total, because they're both going to be in the same volume. So which V total in this case, right? V total, when I open the valve, is going to be the sum of the 2 volumes, 22 plus 72. Okay, and then you'll do the same thing for B. So P1 B times V1 of B is equal to P2 of B times V total. All right, and then your so this one, and you'll have to watch to see. So actually I didn't have to do both of them because it only asks for B in this case. So that's what that problem is asking for. But you'll just double check to see if it asks for the total pressure, then you would just add, I'll add that this one isn't asking for that, but you may see one that asks for that. So P total is going to be P2A plus P2B. You would just add the 2 pressures together. Okay, so there's that one. So actually it won't be the final volume at STP. Okay, so here, so PV equals nRT. And so my final volume is at standard temperature and pressure. So I have 1 solving for my volume, and then 0.0821, and my temperature is 273. So my N is going to equal, in this case, the 5 moles of oxygen, okay, plus then I have argon, so 29.5 grams of argon, and it is 39.9 grams in 1 mole. So however many moles you get, so of the argon. So add those together, and that's what you'll plug in for your moles for that one. Is there anything after that? Okay, I'm not seeing anything after that. Okie dokie. Anybody have any questions over the quest? There is a quest that has some questions over the stuff we did today, which is pretty straightforward. It's a lot of the conceptual type questions as opposed to calculations in there.
I actually don't see the new quest.
Oh, okay. Thank you. Let me look. Maybe I forgot to. Oh, I know what happened. They were having issues. I don't know if they were doing maintenance on the site yesterday, but I do remember now when I tried to work with it, it didn't. Okay, well, I won't keep you while I'm trying to do that, but I'll get that upload or published for you as soon as Quest responds. Oh yeah, it did say it was updating yesterday. Okay, all right, let me go back. I'll stop presenting here. All right, any questions on anything? We'll go, I think what we're gonna do is we'll go through, I will be later today posting your Unit 4 test, the gas law quiz score, and the 2 quests that you did last week. I think those are the only 3 grades we've got outstanding, and I've got them ready to go. I just need to put them in there. For the gas law quiz, I put a Brain Genie goal if you want to re-earn some points on that quiz. So that'll be there. And I'll get later this morning, I'll get those grades in there. Although I think you can see, I thought I set it to where you could see what your score was in Quest on there. All right. Well, email me if you post something to the Jamboard that you need me to look at. Just shoot me an email just to let me know on there, because I think today's going to be kind of busy. So I'm afraid I won't see it today if I need to. All right. You guys have a good day, and I will see you tomorrow. Get my
Hey, Mr. Billy.
Hey.
Sorry, on that last one on the Jamboard that you went over, that's the one I posted.
Uh-huh.
And I didn't, so I added them. I was confused. I didn't know you had to add them, but I still didn't get the right answer.
Okay, give me a second. Let me pull it up. Let's see. Go back to Quest. All right. And let's see. That one is in the gas stoichiometry, right?
No, that's the Dalton's Law.
Oh, okay. Let me go back then. Let's see. Okay. Sorry, they've changed the whole look of Quest, and it's like,
Okay.
I can't find where everything is. Okay,
They
there.
did it threw me off at first too. Oh wait, I just looked at that. I'm sorry. I just typed it into the wrong thing. I did get the right answer.
Oh, good, good, good. Okay.
I just typed it into the wrong one. I do that sometimes.
Okay. All right.
Sorry. Yeah, I
Good
just
deal.
didn't know you had to add them. That's why I put it on the Jamboard. But
Okay.
thank you.
Uh-huh. I'll see you later.
See ya.